Hello students, welcome to series of lectures on digital speech processing. So in this video you'll be able to learn the classroom discussion topic on solutions to the covariance method. So in the previous two videos we have already seen that what is the autocorrelation method. That means we have fixed the interval over which the minimum mean square error can be computed. Okay. So the way how we have already taken the limits for the summation to compute pi n of I comma k, okay, that we have seen for the autocorrelation method by applying the window and choosing the limits for the summation. And when it comes to the covariance method also we have already chosen the limits for summation, right? And when it comes to the autocorrelation method we have chosen the limit starting from 0, okay? But if you choose the values from 0 to some finite value, so there will be a problem for us. What is the problem? So at the beginning and the ending of a window there are large errors that can be possible. Okay, so to overcome the problem, what we are doing, we are going to be choosing the second approach. The second approach we are introducing, that we are calling as a covariance method. In the covariance method, instead of taking the value for summation start from m equal to 0, instead of that we have chosen the previous samples data also. Okay, that means we are going to be choosing the length of a window in such a way that it has to take the previous values below 0. Okay, that is the reason here m is starting from minus I, okay, or minus p samples, where p nothing but the pth order of the linear predictive coding estimation that if you wish to do. So if for instance if you take p equal to 4, so minus 4, the previous 4 samples are also we are including in the length of a window, so that there will be no problem for the estimation of the prediction coefficient at the beginning and ending of a window. Okay, so now when it comes to the solutions to covariance method, right, we have already represented the way how the matrix should be looking for covariance method, so that we can see once again in this video. Let's get started with respect to this. So this is some introduction with respect to linear predictive coding that we already know. The basic idea of the LPC, for every time I am putting this slide, because the basic idea of LPC is very important for us to understand or to predict or to estimate the prediction coefficient of the speech signal. Alright, so the current speech sample can be closely approximated as a linear combination from the past sample. That is the basic idea why we are going to be choosing the linear predictive coding. Now, covariance method, this we have already seen, right? The pi n of I comma k, how we have represented in terms of the matrix form that we can see. This is what I actually am talking about. So m equal to minus p, the previous samples are also we have taken. So therefore, if you want to see the error graph, that will be flattened when it compared to the autocorrelation method. So that is the greatest advantage you will be getting when you look into the covariance method. This is what. So we can also compute the value of alpha by taking the matrix inversion method, but it is somewhat difficult for us. So what we are doing, we are going to be introducing one important method, or the solution to the covariance method is called Cholesky decomposition. Right. So the solution of LPC equations for covariance method is that Cholesky decomposition. This is also very important method how we are going to be solving the values for alpha. So the solution of the matrix equation is called the Cholesky decomposition, or sometimes we can also call this a square root method. So phi is a matrix which is symmetric but not diagonal elements are same. So it is not the toplets. It is symmetric but all the diagonal elements are different. But when it comes to the autocorrelation method, when you want to observe the matrix, row and column and each and every diagonal, all the diagonals are same in autocorrelation method. That matrix we are calling as the toplets. That is symmetric and toplets. But for covariance, it is symmetric but not toplets. So that is what I have mentioned. So what we are doing, instead of pi directly, we are choosing phi equal to A, D, A transpose. What is A? A is nothing but the lower triangular matrix with ones on the main diagonal, whereas D is the diagonal matrix. A transpose is the exact transpose of the lower triangular matrix. Okay. Now we need to determine the elements of A and D by solving for I comma j elements of the matrix equation. This is what, if you take p equal to 4 and the matrix element pi n of I comma j, I am going to be, every time I don't want to write pi n of I comma j. Instead of that, I can write directly 5ij, that is 1 1 1 2 2 1 2 2 3 1 3 2 like that. Okay, so when you take b equal to 4, I starts from 1 to p and j is also starts from 1 to p, and 1 to 4 and 2 to 4. Okay, 1 1 2 1 3 1 4 1 2 1 2 2 like this. This is a 4 by 4 matrix, p cross p, where p equal to 4 in this case, 4 by 4 matrix, and this is A, lower triangular matrix with all the diagonal elements are 1. This is diagonal matrix, and this is a transpose of the first matrix. Okay, if you do the product, you will be getting like this. So this is the way how we need to solve. So by observing that product, we can easily estimate the value of D1 equal to 511, and we can also get a relation for A21. What is the element in the lower triangular matrix? A21 equal to 521 by D1. And similarly, what is A31? 531 by D1. So in the generalized way, we can represent like this. So this dj is equals to 5jj minus something like that, and when ai1 equal to 5i1 by d1, or else this is the equation. Okay, so this is the iterative procedure we need to solve for the values for d3, i4 and all the elements which are there in the matrix. So this is an algorithm. So this algorithm is also very simple when you look into this. Now, so A transpose alpha equal to psi, right? And we are going to be choosing, let psi equal to A into Y, where Y is a column matrix. So that we are going to be calculating all the Y which are there for Y1, Y2, Y3, Y4. This is the relation for each and every element in the column matrix of Y. Okay. Now, what is the generalized way? We are going to be representing Yi should be like this, and this is an algorithm for choosing the value of Y. That's all. Now, so d A transpose alpha equal to Y and A transpose alpha equal to D inverse Y, and where alpha is equals to D inverse Y by A transpose. This is the way how we are computing alpha. So instead of taking D directly, we are going to be taking the inverse of that. It's very simple because D is a diagonal matrix. Because when you take the matrix inversion method before the solution of a covariance method of the Cholesky decomposition, there is this very difficult for us because all the elements we need to do the matrix inversion, but here only the diagonal elements we are going to be doing, and the remaining all are zeros. So that is the way how simple it is. So this is the way how we are going to be computing the reverse order of the alpha. First we are going to be solving alpha 4, 3, 2, 1 and go on. Okay. So this is the way how we are going to be computing the prediction coefficient with the helping of covariance method. And the solution to the matrix of the covariance method is nothing but the Cholesky decomposition. It is very simple. First we have chosen the lower triangular matrix, and then we have multiplied with the diagonal, and then multiplied with the transpose of the lower triangular, and this is the way how we are going to be computing the prediction coefficient. This calculation process backwards from I equal to p minus 1 to 1. Thank you, student. Thank you for watching this video.